When in isolation, an oxygen atom will normally be sp3 hybridized. So if we have something like this, we have four different groups around the oxygen. We have this bond here, a lone pair, and a lone pair. So these count as four different groups. So we need four different orbitals to accommodate them, and so we'd put them in sp3 hybridized orbitals. We use these sp3 hybridized orbitals because it puts all these groups as far away as possible from each other, and so that minimizes the repulsion between the electrons in each of these orbitals. However, when it's possible for oxygen to be in resonance, then it's more favorable for it to be sp2 hybridized so that it can put one of its lone pairs in an empty p orbital, or I guess not empty, it's got a lone pair in it, so in an unhybridized p orbital, and then it's able to participate in resonance through the pi network. So I'm talking about something like, say we have this molecule here with a positive charge at this carbon. Now this carbon here has three groups around it, so it's sp2 hybridized. So this oxygen up here was sp3 hybridized. Now the oxygen, in isolation, we'd expect it to be sp3 hybridized, but here it can stabilize this positive charge through resonance. So this would give us a structure with a double bond between the oxygen and the carbon, a positive charge on the oxygen. And this is a favorable resonance structure because all the atoms in this second resonance structure here, they have a full octet. So in order to be able to donate these electrons over to the carbon, though, that lone pair, this one right here that I moved over, it has to be in an unhybridized p orbital to overlap with the unhybridized p orbital on the positively charged carbon. That's how we make a pi bond. So this is a case when oxygen would be sp2 hybridized. The other cases are also when it's possible to be in resonance but not necessarily next to a positive charge. This would be when it's next to a double bond. So for example, if instead we had this molecule here and put the oxygen on the left there, well, this oxygen, the lone pair could come down here. Now this carbon has too many bonds. At the same time, we're going to have to break a bond, and we could make a resonance structure that looks like this. Now this isn't the best resonance structure because it is putting a positive charge on one oxygen and a negative charge on the other, but it will still have a small contribution. And so this oxygen here in an ester will also be sp2 hybridized, and that's because of its participation in this resonance. To be able to participate in resonance, it has to have an unhybridized p orbital, and so the stability it gains from participating in resonance is bigger than the stability it loses from having the rest of its electrons in sp2 hybridized orbitals, which are closer together than sp3 hybridized orbitals. So those are the reasons why oxygen would be sp2 hybridized when it's able to participate in resonance.